So it's a pleasure to be here again. I guess I've been to Berkeley many times, but never to this part of Berkeley. So it's nice to branch out. So indeed, I'm going to talk about recent work with Ahmed and Shi, who are here, and then with Fernando Pestovsky, Benny Yoshida, and John Presko from Caltech, explaining these connections. So, I won't be able to explain everything, but, hopefully at least you'll be able to get the basic idea by the end of this, and then I'm happy to discuss it more. So usually when I give this talk, I start with AdS CFT, but I guess given the audience today, I decided to start with quantum error correction this time. So indeed, right, quantum error correction, as Daniel explained, you have some Hilbert space. So I guess I'm just going to put in the tensor factorization from the beginning. I guess so I'll be a little bit less general. The Hilbert space is a tensor factorization into n smaller systems, and we can just think of them as qubits. Although maybe in a minute they won't be, but for now let's think of them as qubits. So I defined the code as the code subspace with the correction protocol. Actually, at first I didn't put in the protocol, and I thought Daniel would be mad at me, so I put it in. But then he didn't include it, so that's fine. So we have some code subspace, which I'll call HC, and I'll think of it as being 2 to the k dimensional. So we can think that roughly we have k protected qubits, k logical qubits that we're embedding into n physical qubits. So as Daniel said, I'm today only going to be interested in correcting erasure errors. So that's where we try to recover from the loss of some known collection, which I'll call E, I guess he called it S, of the qubits. And now what do I mean by recover? Well, he wrote it over there, but I'll say it again. So given the code subspace, and then so this I tilde, so tilde here is always going to mean encoded when I write a tilde over something. So the I tilde is just some basis for the code subspace. This is a complete basis for the logical qubits. Then what I'm going to mean by being able to correct for the erasure of E is that there's a unitary transformation acting on E bar. So E bar is the set of qubits that weren't erased, the ones we have in our lab. And I want that unitary transformation to have the property that if I act on any one of these basis states for the code subspace, so you see E bar E here just means that this is the total, this is a state in the Hilbert space of all of the physical qubits. Then I just get back I, so I get back the state of the physical qubits, the logical qubits in this basis on the first k qubits of E bar, and then I get back just some state of the rest of E bar and E, which is independent of I. Okay, so the only difference between what Daniel said really here is that because I'm restricting to erasure errors, I can take the correction protocol to be unitary. I don't have to take it to be a general, a completely positive trace preserving map. So it's something you just given the system, you can put it into your quantum computer and you can implement it. So this is just what I said. So right, the dimensionality of E bar 1 here, this is just, if you like, the first k qubits of E bar, just because we're going to want to put the unencoded message somewhere. Now then the reason why we like that, right, is because now we have some state in the subspace here. This is some protected state. And then we can take that and maybe we lose E, it gets flushed down the toilet or whatever. But we can act with this UE bar on the qubits we do control. And then we just get this state right out here on the first k qubits of E bar sitting in our hands. So this is equivalent to the existence of this U is equivalent to the condition that Daniel gave for the code being correctable. Now, actually, here's another equivalent definition, one that's better suited for my purposes, although maybe it seems a little bit more formal at first. So say that I have some operator O tilde. So again, tilde, remember, means encoded. So it's some operator that implements a logical transformation within the code subspace with these matrix elements. But this O tilde, right, it's in general, it's just could be some complicated operator acting on all the physical qubits. But I want to, it implements some transformation on the code subspace, and I'll insist also that its Hermitian conjugate also implements the conjugate transformation on the subspace, so it doesn't have any funny off-diagonal elements. So here's the equivalent definition. So we can correct for the erasure of a subset E if and only if for any O tilde, so for any such O tilde, there always exists an operator O E bar which acts just on E bar, on the qubits that we do have access to, and which implements this O tilde and whose dagger implements O tilde dagger. So if you like, this is just saying that if the code is correctable, then any logical operation on the Hilbert space, on the code subspace, can be implemented just by an operator on E bar. So this is sort of, this is related to this idea that E has no information about the system.
Sorry, so do you allow this OE bar to be a function of not only O tilde, but a function of psi? Like when I choose different.
Absolutely not.
No.
Absolutely not. No. In the same way that I don't allow the correction procedure to depend on the state. I mean, if it did, then it would be nonlinear evolution, and it wouldn't be something we could do with the quantum computer. We'd have to learn how to violate quantum mechanics to do it. There are actually people who like to do that in our field, but this particular violation. But that's not what I'm doing today. Okay. So yeah, sorry, this is a little bit dry, but I thought it's good to just get this out there clearly, and it helps that Daniel already discussed this in his talk.
And why would you say that E doesn't have any information? I mean, wouldn't you say something like whatever information E has is redundant, it's already contained in psi tilde? Yeah,
right. But then so I guess I was sort of implicitly using something like the no cloning theorem in my head. So if I can, what this is roughly saying is that sort of any observable. Any observable that acts within the code subspace, I can measure sort of by measuring an analogous operator that acts just on E bar, on the part that didn't get erased. Yeah, and then it's a homework problem to convince yourself that this statement is equivalent to the existence of this U. Okay. Okay, now I'm going to give an example, because I think we've all been sort of formal. So here's a very concrete example. So actually, this is where I learned about this. Is this actually where it was invented? Okay, so I got that right. So this is maybe the simplest example of a quantum error correcting code. I just want to embed a single logical Q-trit, so that's a 3-state qubit, into 3 physical Q-trits. And now the annoying thing about this model is that 3 appears in 2 logically distinct places. So just bear with me. There's 3 physical Q-trits, and the code subspace is 3-dimensional, and in principle those are unrelated. Okay. So here's some state that in the code subspace, and then the idea is that we pick this subspace. This is a subspace that we pick. So the reason why there are several reasons why we like this subspace. One is that it's sort of obviously symmetric between the 3 physical Q-trits, right, under permutations of the Q-trits. But also, the important thing, as Daniel already explained, is that any state in this subspace is maximally mixed on any one of the Q-traits. So any one of the Q-traits has no information about the state. Okay. Now, the reason that's nice is because we can define this U now like this, right? So let's say that it's the 3rd Q-trit that gets erased. Okay, so now we're going to try and construct a U just on the first 2. So a U12. So okay, I claim another homework problem. Well, actually, it would be a better homework problem if I didn't tell you the answer. But I claim that the U12 that acts on the first 2 Q-trits like this indeed has the property that if I act on any one of these, these 3 states, right, then I just write I, the 0, 1, or 2 here, onto the first Q-trit, and I get this state chi here on the second 2. And now, so if you're actually doing this, I send you these 3 Q-trits in the mail, and the 3rd one gets lost. Well, you don't have the 3rd one, so when you but you do have the first 2. So you implement this U12 on it, and then what you're left with is some maximally mixed density matrix on the second one, which you can just flush down the toilet or something, because you've got the state back on the first one. Okay. And then because the subspace is symmetric, right, clearly there's also going to be a U13 and a U23. So we're going to be able to recover the state on any two, using any two of the three Q-traits. So this is sort of the simplest example of the general thing that Daniel was talking about. Okay. And please ask questions. I mean, I know this is kind of a freight train, but I'm happy to be stopped at any point. Okay. Now, in the model, we can also understand, so this was the sort of state recoverability definition of correctability, but I also gave this other definition in terms of reconstructing the logical operators just on the part that didn't get erased. So we can see that work here too. So say O tilde, is one of these operators that acts within the code subspace. Well, I can do this, right? So I can define a new operator, O12, where I first act with this U12, so that decodes the message onto the first Q-trait. Now, while the message is in the first Q-trait, I act with this O1. So I act with the unencoded version of the operator. I just act with the single Q-trait operator with those matrix elements. And then I re-encode with U12 dagger. And so this is some operator that acts within the code subspace in however I like. So I can put in sort of arbitrary matrix elements here for how this guy acts within the code subspace. And I can always do this construction. And actually, this isn't special to the model. I mean, this was true in the more general discussion also. This is how you relate these two notions of correctability. And then so as before, right, because the U13 and the U23 also exist, there's also going to be a O13 and an O23. Okay, so that I can represent these logical operations on any two of the Q-traits. Okay, so that was all I was going to say about quantum error correcting code. So if there were any sort of things that you didn't get from Daniel's talk, or if this isn't clear, ask now. Otherwise, it's on to gravity. Okay. All right, so now let's try and relate this to AdS CFT. So Patrick said some of these things in his talk this morning, so sorry, I'll just say them again. Maybe in a slightly different way. So this is the metric for anti-de Sitter space. If you've never seen a metric before, this probably isn't that illuminating, but t is some time coordinate. This symbol means coordinates on a sphere of dimension d-1, and this r is some radial direction. The picture is like this, right? So anti-de Sitter space is like the world in a tin can. So this is r equals 0 in the center. R goes out this way, T goes up this way, and then the sphere directions kind of go around. And like Patrick said, it has the nice property that if you're sitting in the center and you shoot a laser pointer away from you, it goes out to the boundary and comes back to you in finite time. So it's sort of like quantum gravity in a box, if you like. This is the sort of infinite square well of quantum gravity. Maybe the simple harmonic oscillator is a better analogy. Okay. Now, this geometry, of course, is just empty AdS. So if that was all there was to the world, it would be a very boring theory of quantum gravity. It would have one state and nothing would happen in it. So to get an interesting theory, we need to have more states. So the idea is we define these asymptotically AdS states where they differ from this geometry at finite values of this radial coordinate, because we put a person there and the geometry was responding to that. But then at large enough R, the geometry comes back to this AdS form. Now, it's very important here that in this setting that, right, as this R goes to infinity, right, so since the geometry just becomes like this, and then at large R, if we look at the metric that's induced, at the geometry that's induced on a fixed R slice, right, then we get this sphere and we get this time, and they're both multiplied by the R squared at large R. So the geometry just becomes a sphere times a line. So there's the boundary sphere and there's time. Okay. So what? Well, the so what is that then we have this great proposal from Maldacena that quantum gravity in these asymptotically AdS spacetimes is really defined non-perturbatively as a conformal field theory which is living on this boundary of the cylinder, or boundary cylinder, I guess it depends on your term. Okay, so now, precisely defined, what does that mean exactly? Well, here's what it means. So there's a dictionary that relates things in the two sides. So first of all, the Hilbert spaces are equivalent. So any state in the CFT, any state whatsoever, has a bulk interpretation. It has some interpretation, as some type of excitation of Antide de Sitter space. And vice versa, although the vice versa isn't so clear, since really probably it's better to think of it as a definition from the CFT to the bulk. The Hamiltonians are the same, as are the other generators of the symmetries. So the states fall into the same representations. The eigenvalues of the Hamiltonian in the CFT are the eigenvalues of the Hamiltonian in the bulk theory that it defines. But then the real, so these are sort of formal. The real meat comes from a relationship between fields in the bulk and local operators in the conformal field theory. This is the relationship. So you take a field, right? So a field in the bulk is going to depend on all three of these coordinates. And then the idea is we extrapolate the field, taking r going to infinity and rescaling by something. This delta is the conformal dimension of this operator. And we get some local operator. So see, now it just depends on time in the sphere. So it's on this r times the sphere that the CFT is living on. And this is supposed to be an operator equation. This equality is supposed to hold in any state. Okay, so so all three of these statements are quantum statements. And I want to emphasize that because often you go to talks about AdS CFT and all they're doing is solving classical gravity equations. So I mean, this is the quantum statement of the duality. Okay. Now, the way that quantum error correction is going to get involved is that we're going to try and, was there a question? No, okay. And please stop me if there are questions. The way quantum error correction is going to appear is that we're going to try and do something which is called sub-region duality. So that's something that, several people in the audience were really among the first people to think about. There were a couple papers from Berkeley by Raphael, Ben, Stefan, Vlad, and Claire. And then also Bartek with Mark. And then I actually don't know who these two people are. I don't know. Who are they?
Joanna Kaczmarek is a professor at UBC. She was a postdoc with Andy's Challenger.
Okay.
And Fernando Nogueira quit physics since then, but he was Mark van Ramstang's student.
I see. Okay, good. So yes. So this was something maybe four years ago now, maybe 3 or 4 years ago, these people were thinking about. The idea, said sort of in a more computer scientist-friendly way, is say we're given access to the quantum state of only a sub-region of the CFT. So remember, the CFT is a quantum field theory on a sphere. So the Hilbert space is spanned by field configurations on a sphere. It's a tensor product of different parts of the sphere. We give you the reduced density matrix just of the quantum state on some part of the sphere, say the north hemisphere or something. And then we ask, is there a subregion of the bulk that we can still learn about? Or in other words, is there quantum information about the bulk which we still have access to, even though we only have a sub-factor of the Hilbert space of the conformal field theory? So said this way, this is sort of very obviously an error correction question, right? We erase part of the sphere, and we're trying to see if we can still recover information from the part that we didn't erase. Okay. Now, in fact, not only is it an error correction question, it's an error correction question that has an answer, or at least a partial answer, which was explained by these people. Strictly in the bulk, using machinery which is not totally clear from the CFT point of view, so by solving the bulk equations of motion as operator equations, perturbatively in the 1/n expansion, which is not a very natural set of words if I just handed you a spin system, but in the bulk it's very natural, you arrive at this sort of remarkable kind of formula. So we're going to now have to spend a sec unpacking the picture and the formula. So the cylinder here, again, is Antide de Sitter space. This point x is some point in the bulk. And we're going to be interested in a bulk field phi of x, which is located at that point x. Okay? And so intuitively, you can think of this phi of x as a logical operator, just for reference. Now, the claim is that, now I also have to introduce this a here is going to be a subregion of the boundary. So this circle, I'm doing AdS 3, so the boundary is on a single circle times time. So a subregion of a circle, well, at least if it's connected, it's an interval. So this A is associated with a subfactor of the Hilbert space in the quantum field theory. Okay? Now, according to this subfactor, or this subregion, or to this subregion, there's a sort of messy way of associating a region in the bulk, which I've indicated by this figure. I won't describe it in detail, but roughly you take this A, you construct this green diamond in the boundary, which is called D of A, and then you look at sort of the intersection of the future of D of A and the past of D of A. And that describes this sort of wedge of cheese here, which sort of lies in between this curve here and these dashed lines and this green diamond. It's a wedge, like a wedge. And now, okay, the claim is that if X lies in this wedge, this W of A, then it has a representation in the conformal field theory where in the conformal field theory, the support of the representation, so this O is some local operator. I'm integrating this local operator over this D of A, this green diamond, and only over the green diamond. So it means that this operator, indeed, this logical operator, if you like, has a representation just on A. Okay? So it has so in other words, if I erased A bar, that wouldn't bother me. I could still implement this logical operator by acting with this representation of it.
So are you going to distinguish between the entanglement wedge and the causal wedge?
No, I'm actually going to carefully not distinguish between those. Yeah. So hold your horses. Yes.
Sorry, it's a naive question. I thought their approach involves some kind of first rotating this direction to a time direction. And
no, that's the wrong way. Well, yes, it's true they like to say those words, but you don't have to say those words. You can say them in the way that I said.
So I don't need to do any analytic continuation?
No, you just have to understand that this K should be interpreted as a distribution. It's not really a function. It's a distribution, but that's fine.
What's the difference between distribution and function?
A distribution is not a function. A function is a special case of a distribution.
You have to integrate against it to make sense of it.
Yeah, you have to integrate it against something. It's a linear map from the space of functions to complex numbers.
Delta function is a distribution, that's not a function.
That's right, yeah. Yes.
So for it to be a quantum error correcting code, you need that if you erase like a small area of the cylinder, no matter which X you take inside, you can always recover it from the complement.
Good, so I'm gonna explain a lot more about that in a sec. Yeah, okay. This is just to give you a sense that the point of this is just that there's some operation which is fairly natural from the bulk point of view, which looks a lot like this reconstruction of logical operators. To make the connection precise, I'm going to have to tell you what's the code subspace, and what are really the logical operators and so on, which I will in a sec. But this should already be reminiscent at least.
So is the statement then for a point X deeper and deeper in the bulk, you're more and more sensitive to erasure, information erasure on the surface?
The opposite. You're better and better protected.
Better and better.
Yeah, I'm going to emphasize that in a sec, though. So just once. That's sort of the same as what he was asking. Yeah. That's right. Okay. So this is kind of messy. This is more intuitive from above. So let's just take this slice here, this spatial slice through the bulk whose boundary is this circle, and let's just look at it from the top. Okay, that's what Daniel was drawing over here. So then this A is this interval here, right? And then from this A we can define this wedge region, which I'll call the causal wedge. Just a name. And then the claim is that this phi of x, where x is inside of here, has a representation in the CFT on the region A. But this y, which over here is outside of the wedge, does not have a representation in the CFT on A. That's the lesson you should remember.
Sorry, what is exactly phi of x and phi of y?
These are, they're operators. They're local operators that depend on that point. So in a quantum field theory,
that point, or
they act in the Hilbert space only on the tensor factor at that point. that's what you would say in a quantum field theory. Here they're in the bulk, so it's not totally clear that those words make sense. But yes, morally that's right. Yeah, they're operator. If you like, they're just operators labeled by a point in the bulk. Yeah. Okay. So using this kind of, so this is called the Rindler representation of the operator. So we can using it we can reproduce. So we reproduce one feature of quantum error correction. Here I'll reproduce another. So here I cut the boundary into 3 pieces, A, B, and C. And now let's look at this guy in the center here. So this guy in the center, it's not in the causal wedge of A, nor the causal wedge of B, nor the causal wedge of C. So it has no representation just in A, B, or C. But it does have a representation in either AB or BC or AC. Okay? So this is very reminiscent of what was happening in the Q-trit model, right? Where the logical operators I could represent on 1 and 2 or 2 and 3 or 1 and 3. Okay. But here we see it just coming out of solving wave equations and doing quantum field theory in curved space time.
So in this case, the logical operators are not all the operators in the bulk, but only in this region in the middle.
Yeah. For this case, this is like sort of this is like the simple here. Yeah. Let's just say there's only one. There's one logical operator in the center or something. Yeah. I mean, the model I'm going to explain in a sec will have more, but this is sort of a the same kind of thing we see at least is happening here as happened in the 3 Q-trit code. Okay, so now this is related to what Catherine was asking. So indeed, we see that we have this nice feature that operators near the boundary are less well protected than operators near the center. So for example, this dot in the center, say I have this big green erasure here, well, so what? I can just reconstruct it going around this way, right? Or this big one here, well, I can just reconstruct it going around that way. So it's actually protected against quite large erasures. Whereas this one over here near the boundary, well, this tiny little red erasure is already enough to kill it. Okay, so if you like, there's a sort of a nice sort of map between the sort of radial direction and the well protectedness of the operators. And this should be reminiscent of the people like to say actually in AdS CFT there's a relationship between the radial direction and sort of scale in the boundary theory. This is a sort of very precise illustration of that. Usually it's sort of a more of an emotional statement. Okay, now, oh, oops, I forgot some pauses here. Okay, so in the paper with Shi and Ahmed, we thought a lot about how to say this more explicitly, how to really, in the CFT, tell you what's the code subspace, or what are some interesting set of code subspaces, what are the errors. There are some interesting subtleties, some of which involve sort of generalizing what you mean by quantum error correction. But in the end, there's sort of a limit to how much you can say because it's a strongly coupled CFT, and in the end, you just can't compute everything that you'd be interested in knowing. So more recently with Fernando, Benny, and John, so I guess we love our acronym. This is the acronym for the paper. We were able to come up with a rather explicit set of codes, which are actually stabilizer codes, which is the word I'm not supposed to use. So it's OK, I won't use it again, I promise. Which are generated by tensor networks, which is a word that I am supposed to use. And which illustrate sort of many of the features that we sort of more implicitly decided that must be there in AdS CFT. So the way things work in the model is basically sort of it all works as we thought it was going to work, but it's much easier to explain because it's discrete and it's totally precise. So actually, I'm just going to explain the discrete model rather than trying to tell you how to embed these things into the into the CFT. This is probably better for the computer scientists anyway. Okay, so the idea is that we're going to replace the model. We're going to replace the CFT by just a chain of n qubits. Okay, n qubits. And then, I'll consider a 2 to the k dimensional subspace of states of the qubits, and I'm going to interpret the subspace as corresponding to the set of low energy states in the conformal field theory, where by low energy, I mean energy less than n squared. If we were talking about n equals 4 super Yang Mills, this big capital N squared, or if we were doing 1 + 1 dimensions, it would be energy that's low compared to the central charge. where, to be clear, the units are made up by the radius of the sphere, so the central charge in units of the size of the spatial sphere. Okay. So I'm going to build this subspace by a tensor network. So the tensor network, after I've contracted everything, I'll show you the tensor network in a minute, but after I've contracted everything, it'll just be some one big tensor where there'll be n sort of output legs and k input legs. And then I'll interpret that as defining a subspace in the Hilbert space of the output legs, right? So this guy on the right here, maybe I should have put a tilde here to be consistent with my previous notation. I apologize. The subspace here, this is the wave function in the physical qubits of the states in the code subspace, and it's defined by this tensor. Okay. Now, the tensors I'm going to use to build the network are not just going to be any old tensors. They're going to be very special tensors. Now, in some sense, that's bad because then it makes it sound like whatever I'm going to say is going to be very finely tuned. On the other hand, I would just say my goal here is to come up with the simplest possible thing. I'm not going for genericity here. I think many of these things will still roughly be true if the tensors are random. I think Brian and she and Ahmed are working on that or discussing that. But I'm just going to give the case where I choose the tensors sort of optimally, whatever the opposite of adversarially is, friendly. Yeah.
So is it what you are doing here is just like a reformulation of what we have heard, like previously in the language of error correcting codes, or is there something to construct beyond what we have heard?
Well, I'm not sure what to say. I mean, so the code I'm going to describe is a stabilizer code. So in that sense, it's Daniel invented it, however many years ago. But it's not the kind of stabilizer code that people usually think about. So in some sense, it's a new kind of stabilizer code.
You said it 3 more times. I'm going to ask.
Oh my God, sorry. No, but it was purely a sociological comment.
Sounds too cool for us not to know.
Can I tell you at the end? I promise I'm not going to use it.
But isn't it just ground state of Hamiltonian, which has a commuting projector?
No. Stabilizer codes have a special Pauli structure. Okay, fine. You have n qubits. There's a group of products of Paulis acting on all of the qubits. You pick an abelian subgroup, which you call the. You pick an abelian subgroup. No, they do not all commute. X does not commute with Z. So there's the non-abelian group of products of Paulis on all of the qubits. You pick some abelian subgroup, just however you want to pick it. And then so any product of Paulis, its eigenvalues are plus or minus 1. You look at the subspace, which is plus 1. Okay, and that defines the code subspace. That's a stabilizer code.
Particular choice, but more generally, what I said is right. It's just a ground state space of Hamiltonian with commuting projector.
Yeah, but it's particular type.
There are very special kinds of projectors made out of Paulis. Yeah, that was what I was trying to emphasize. Yeah.
So I was trying to wrap my head around this issue of you have a code in which some information in those closed wedges to the boundary is encodable locally, meaning it's the opposite of what we think about as error correcting code.
So
your logical information is actually the point in the middle.
That's right. So if you want, so the code I'm about to describe is not going to be a good code. To make it a good code, you have to turn it into a subsystem code, where you only view a subsystem of the code subspace as being the set of things you care about. So, but it'll be more clear in a minute, I think, right? There's some freedom to you what you consider logical operators and what you consider errors. So here I guess the way I chose to define the code subspace here is defined to make high-energy physicists happy. But unfortunately, therefore, it makes computer scientists unhappy because it's a bad code. So when we wrote our first paper, we defined the code subspaces so they would be good codes. And then we had to deal with all sorts of confusion from high-energy physicists who couldn't understand why we defined the codes that way. So here I inverted it. So I'm sorry, but it'll be more clear once you see the model, I think. Okay. I'm going to build I want to build this big tensor. I'm going to build it with a tensor network. And so, unlike most tensor network talks, I'm going to tell you what the tensors are. What the tensors are going to be Sorry, Bartek. So I'm going to pick the tensors to be what are called perfect tensors. So perfect tensors is a tensor with 2n indices, an even number of indices. But it has, each index has the same range. But they have the special sort of almost magical property that any balanced bipartition, meaning any split into n and n of the indices, gives you a unitary transformation. Okay, I claim tensors with this property exist. Okay,
N.
What? For any n, I think it depends what you do with the range. I think if you're willing to play, oh yeah, you would know this. Yeah, probably. If you're willing to play with the range, maybe I think it exists for any n. But I mean, if you pick the range and n, then it doesn't always work. Actually, right, it's not obvious that these exist, and they're sort of intimately related to error correcting codes.
Say if I don't care, I don't need to. If I don't worry that the range is too high, say I always allow the range to be high. Is there a program that I input the n and it gives me a code?
We should ask Daniel that question. So this is like whether or not are there threshold
dimension.
Yeah. So are there nk threshold schemes with any n and k as long as you allow d to be large?
No, k has to be at least n over 2, basically.
Sorry, yeah, that's right, up to that.
But yes, and you can do
yes.
it.
Yes. Okay. Yes.
Dorit and Michael.
Yeah, that's what I thought. So that's why I said you would know.
They're based on classical Reed-Solomon codes. So
I see. So there is a program which just do that.
Well, it's not. I mean, it's easier to write them down. It's
Okay.
Yeah.
Yeah, but I'm not sure what's
Okay. So let me just give you one example of it. Are we okay? Yeah. So let me give you an example of such a tensor. So the 3 qubit code that I defined earlier is actually gives you an example of such a tensor. So here I remembered the tilde. So you just take the wave function of each of these states that I wrote down earlier, and that defines a 4-index object. And I claim that this object has this property. And it's that it follows from the, so it basically it follows from the fact that this U existed, and that there's what Daniel mentioned, that on any one of the qubits it was maximally mixed, not just independent of I, but maximally mixed. That was important in getting this property. Okay, so I guess these things are also in one-to-one correspondence with what are called absolutely maximally entangled states, which are states where any subsystem is maximally mixed. So if you have one of those, then that's equivalent to having one of these. And from that, you can also produce a quantum secret sharing scheme. Okay, anyway. So actually, the tensor I'm going to use today, though, is not going to be this one. It's going to be this one. It's going to be based on the 5-qubit code. So the 5-qubit code gives you a 6-index. The encoding tensor for the 5-qubit code is a 6-index tensor where each index runs from 0 to 1. Okay, so it's qubits. Okay, so these are just the tensors that I like, and that's a very specific one. Okay. Now, perfect tensors, they have this nice property that, yeah.
How general is this relation that, whenever you have an n-qubit code encoding, m qubits, that you can take the inner product between the
yeah, so good. So it goes one way. So anytime you have a perfect tensor, you can make a beautiful quantum error correcting code. It doesn't always go the other way. You need, because remember,
for only one bipartition, or for is there
any
discrete?
Yeah. So what you more precisely, you need what's called these threshold secret sharing schemes, which are special cases of erasure correcting codes. The thing you need is that there aren't collections of qubits with partial information about the state. That's the thing that can get you into trouble. So in
Why is that troublesome?
Well, I guess because with a secret sharing scheme, right, you want any group of people collection of the shares to either have no information or all the information. I mean, I guess that's the definition, but
why is it troublesome for you?
Oh, well, yeah, I'd have to stare at it again, but I mean, because I think this thing about, right, you really want maximal entanglement. Like to get it to be unitary, like unitary is a very strong thing, right? You want U dagger U to be 1. And so roughly U dagger U corresponds to, if you take one of these tensors and you write down u dagger u equals 1, and then you move one of the inputs, so if you take one of these tensors and you move one of the inputs to the outputs to get an isometry, and then you contract them, right? Then you'll still get an identity. So like say I take the 6th one, but then I interpret this in isometry from 2 to 4, okay? Now that's an isometry from the 2 to the 4. So if I do t dagger t, then I should get a delta, the identity map on 2 qubits. But that's the reduced density, that ends up being the reduced density matrix on 2 of the qubits, and it's saying that it's maximally mixed. And and I want that to be true, right? Like all the way until I get to enough qubits that I know everything, right? Sorry, I think this is getting too technical, so I'm sorry. Yeah?
Is there a simple reason why you're not going, why using full index tensors would not work?
Yes. It's a bad code. If you use it in the way that I'm going to use it, it's a bad code because the lattice in the bulk is a tree. It's the beta lattice, and that's a bad code. There's a tiny little erasure that deletes the central qubit.
But there's no particular reason why 8 index.
No. 5 is not unique here. It's just 5 was the smallest number that worked. Okay. All right. So now these perfect tensors, they have this nice property that, so say I've got a perfect tensor here, so by this I mean half the indices. So say this is 3 indices and this is 3 indices, and I have some operator that I'm contracting with half of the indices. Then I can replace it by another operator contracted with the other 3 indices just by doing this stupid thing, right? So O prime I define as t dagger OT, and then I take this and I substitute it here and I get that. So this means that any operator contracted with any 3 of the indices, I can push it through the tensor and turn it into an operator acting on the other 3. And by the perfection, I can do that from any 3 to any 3. Yeah.
Is T the perfect one here?
Yeah, T is the perfect one here. Yeah, that's right. Yeah, actually, to write this formula, had I replaced dagger by inverse, it would have been enough that it was invertible. But the unitarity is convenient for other things, which I may or may not explain explicitly. Yeah, I mean, although I must say that morally I agree with Douglas's comment before that the tensor shouldn't actually be unitary. But here for me, it's a matter of convenience.
How are you doing on time, just so we have time for
almost there. Yeah, almost there. Yeah. Okay. Right. So yeah, well, I already said this, but so these T's therefore give isometries, meaning inner product preserving linear maps from any collection of at most half of their legs to the remaining legs. Okay. That's another property of perfect tensors. All right, enough. Onto the model. So now the idea is that I'm going to take the hyperbolic plane and I'm going to tile it with pentagons. So that's sort of this white and gray in the background here, or I guess the blue things, right? Each pentagon I'm going to interpret as I'm going to stick one of these 6 index tensors there. 5 of the legs I'm going to contract with the neighbors. And then the 6th one, which is indicated by this red dot, I'm going to leave free. Okay? And then I'll go out to some fixed radius, and then I'll shoot all the remaining guys out. And now I'm going to interpret this as my big tensor, where it's a map from the ingoing red dots to the outgoing white dots. So this is going to define a subspace of the boundary Hilbert space. Okay? Now, why do I like that? Well, here's why. So say I've got now, this is how my collaborator draws the picture. This is how I draw the picture. So say I've got some operator acting on this dangling leg in the center. Okay? So by pushing it through the whole map, by pushing it through the entire map, it defines some non-local operator in the boundary. But we can see how that works very explicitly, right? So I can view this guy, as an operator that acts on this leg and the identity on these 2 legs. So then I can use the pushing operation to move it onto an operator that acts on these 3 legs. Now I can do that again here. So I can push this one to here, here, and here, right? This one to here, here, and here, right? And so on. I can keep going. And eventually I'll construct some very non-local operator that acts directly on the boundary qubits, the physical qubits, which acts within the code subspace in exactly the same way that this operator here would have acted in the logical Hilbert space. So this is like this Rindler reconstruction, right? I'm reconstructing this operator on some subregion of the boundary. Yes?
Why does the pushing have a direction? So I understand that. So there's just some objective?
No, it doesn't in general. It's just because I'm starting with a bulk operator and I want to push it out. There's not an inherent directionality in the graph. The graph is undirected. Okay. Now.
How does it become any? Why are you pushing out along 3 legs from the center and not?
Yeah, because remember these tensors. I was using this operation. So an operation on any 3 legs can go to any other 3. So I was choosing to view this one and these 2 as the inputs, and I was pushing onto these 3 outputs. But as I think some of you were already guessing, though, this is going to be non-unique, right? Because I chose to do that, but I could have easily sent it this way, and that way instead. And then I would have come up with some representation of the operator, down here, right? Or I could have picked these 3, and then I would have come up with some representation of the operator over here.
They don't have to be adjacent, right? You could have picked 3.
In fact, yes. So were I discussing the issue that Bartek brought up, then I could send it this way, and that way. That's correct. Yeah. Okay. 1 sentence. In this model, you can reconstruct the entanglement wedge, not just the causal wedge. Okay. I'm happy to discuss that with the experts later. Now, you can also see, right, so you can see this non-uniqueness is exactly what we expected from the AdS-Rindler reconstruction, right? So right, there's some wedge here where I can make this. There's also some other wedge here where I can make it. You also see that operators that are closer to the boundary, I can reconstruct in smaller wedges, right? So that's also the same as what we got from solving the bulk wave equation. Okay. Now, maybe I'll just comment. So these seem to be on some level a new family of quantum error correcting codes. So they're like concatenated codes, which I guess are standard, but they have loops, right? You see, so sometimes inputs get contracted with other inputs, and the perfection of the tensors makes that okay. It preserves the isometry property. So each of these is undirected. So it's a new set, a broader set of codes. It's interesting to think maybe they're good for something. Maybe they have a better threshold than the usual concatenated codes. Yeah, is that a question?
So when you push it this way, say if I don't consider the 2, the one that split it in 2 regions, just the 1 region case, is there a reason that the border of this this region is geodesic? The one in the previous
sorry, you mean? So to ask that question, you should ask it the other way. You should say, if I pick a boundary subregion, and then I ask what set of tensors can I reconstruct, is it bounded by a geodesic? I think the answer is yes. There's an algorithm given the boundary region to generate a set of these guys which are correctable. We call it the greedy algorithm, which to physicists sounds silly, but it's a standard term in computer science. And its boundary is a geodesic. Yeah. Okay. Now, so maybe these are good for something. Indeed, let me comment. So the code I've literally described here actually doesn't literally have a threshold.
What's a threshold?
Good. So a threshold is, so say that with each boundary qubit, there's a probability p that I erase it. Okay? A threshold is the statement that there is some finite order 1 probability p, such that if p is less than, let's call it p critical, and if p is less than p critical, then I can correct, for example, the central qubit, for example, I can correct to sort of exponentially good precision. So as I make the system size bigger, it gets better and better protected in a way that goes exponential in the system size. So good codes usually have this property.
In the worst case.
What? No, that's typical case. That's the difference between threshold and distance.
Distance is the worst case.
Distance is the worst case. Yeah. Okay. So this one actually doesn't have a threshold. There's an order 1 number of erasures that kills the center. But there are simple generalizations that do. They illustrate the sort of AdS CFT aspects of things just as well, but are a little more complicated. So I explained this one instead. But actually, and indeed, if you do want to protect only a single qubit, it seems that you can get the threshold all the way up to 1/2, which is the theoretical, sort of theoretical upper bound on how big it can be. Okay, now last slide. Second to last slide. So you might ask what happened to the rest of the Hilbert space. So here I'm constructing just this tiny Hilbert space. So, well, I quoted the result before. The dimensionality of this is 2 to the is 2 to the 1 over square root of 5 times the total number of boundary qubits. So that's a very small fraction of the boundary Hilbert space, whereas I claimed in the beginning that in AdS CFT, every state in the CFT needs to have a bulk interpretation. So clearly we're going to have to account for the rest of the states somehow. My claim is that I can account for them as black holes. The way I make a black hole is I remove tensors. So say I remove the central tensor. Well, before there was one dangling leg there, but after I remove it, now there are 5, because there are all 5 of these. And so now the subspace has gotten bigger by doing that. And so a little bit of it were the ones that I would have already had anyway, but I take the orthogonal complement and I interpret that as a black hole of whose size is 1 AdS radius. I can make the black hole bigger by removing the next layer of tensors. And so clearly as I do that, the entropy, the dimensionality, the log of the dimensionality will grow like the area of the boundary of the region where I removed the tensors. And if I keep going and I get all the way out to the boundary, then I've removed all the tensors and I'm back to the identity map, which means I've accounted for the entire Hilbert space this way. And at any finite size of the black hole, it's clear I can still describe all the operators outside just fine by doing the pushing outside of the horizon out to the boundary. OK, now really the last slide, I promise. Does that mean there are firewalls? I guess someone should talk about this. See, I've said that I've removed the interior of the black hole. Unfortunately, not necessarily, because this whole thing, I'm sort of only working on the AdS scale sized regions. And these big AdS black holes have this funny property that if you jump into them, you die in an AdS time, no matter how big the black hole is, which means that whether or not there's an interior in these models would require me to first understand how to understand sub-AdS physics, which is a thing that I don't really know how to think about in these models. In fact, it's one of a number of things that I don't know how to think about in these models, so maybe I'll just list them in case people want to discuss them, and then I'll stop. So no boundary translation invariance. That central tensor has 5 legs, so I've broken the continuous rotation symmetry at the boundary to Z5. Z5 is not a very large group, so there's no sense in which there's approximate translation invariance except at a very crude level. There's no dynamics. I didn't tell you what the Hamiltonian is. Now, I told you a little bit about the Hamiltonian because I told you what the set of low energy states was, but that's a sort of crude thing to tell you about the Hamiltonian. It would be nice to know more. There's no bulk diffeomorphism invariance. I mentioned that at the beginning, or earlier today. Well, I already said this. There's no sub-AdS scale locality. Nonetheless, I think these models are nice. They're very concrete. They illustrate sort of the error-correcting properties of AdS CFT that we sort of convinced ourselves that it should have. It would be nice to see if we could include some of these features. Obviously, so presumably the CFT itself defines an error-correcting code which does have all of these features. And eventually, if we want all of them, we're probably just going to have to go to that. But maybe we can learn more by sort of inching our way in that direction. OK, now I'm done. Thanks.
I'm wondering whether when you want to study the interior of black hole, then even if I have a sub-AdS scale, does that also require to have the description of the dynamic?
Have what?
The dynamics, the other.
Yeah, it might, yeah.
So
I think, the sub-AdS locality is a subset of the things you would need to understand. Yeah, probably.
So another question also related to the sub-AdS thing is, when you go back to this formula of Hamilton et al., you write the bulk field as a function of boundary. Then I can move the bulk location a little bit by something smaller than AdS radius.
Yeah. So good. So in this formula, there's no problem with sub-AdS locality. So sub-AdS locality is taken care of here.
The commutative relation can work.
What?
So I can have different facts all commuting with each other at different spatial locations in the bulk.
Yeah.
Which seems to indicate a much bigger space.
Yeah, but you only get that commutation working within a subspace of states. So they only checked the commutators in the sets of states where you act on the vacuum with some order 1 number of bulk fields. And I would claim it won't work. I mean, usually when I give this talk, I make a lot of hay about the algebra of bulk fields and how it can't be realized in the CFT. I chose not to do it this time, but yes, anything you think about like space-like commutators in the bulk is going to have to break at the level of the operator equations.
In your version, in the follow of the code, something like this do not.
No, you see it, because what happens is the operators end up behind the black hole horizon before their algebra is going to break. So as long as they're still outside the black hole, the algebra works. Which is how we said things should work in our first paper. But I mean, in the model you can see it very explicitly.
So if you have the code where all the red dots are logical qubits,
yeah,
that has a very bad distance because the ones right near the boundary are very sensitive.
That's correct.
So okay, so now let's convert it to a subsystem code
where we just include, say, these ones.
Qubits, we don't care what happens to them.
Yeah, that's right.
Qubits.
Right.
And so what happens to the distance then?
So it goes up. So we studied that by using the threshold, because distance was somehow we couldn't figure out how to compute the distance. But with the threshold, so that's what I was going to comment on. So in this code, it's actually still bad because it's not totally obvious. But in fact, so you see like these 2 points right here. So you see this thing here. There's like these 2 lines that go this way. If I screw up these 2 points. And these two, if I just use these 2 points and these 2 points, here, these two, I can actually make a logical operator on the central qubit. And it's only 4 points. So the distance is still order 1. But so in the paper, that's why we introduced a generalization of this, where layer by layer, you alternate between pentagons and hexagons, where the hexagons don't have any dangling legs. So you introduce a less symmetric tiling with 5, 6, 5, 6 going out. And then that one has a threshold, which is order 1. Like, so if you erase, like, I forget, it's like less than 20% or something, you're in good shape. And if you want to go, and then the furthest you can go in that direction is you take only the center one to be a pentagon, and you take the rest to be hexagons. So now it's a map just from one of these to all of the boundary legs. And then for that one, the threshold seems to be a half. So you can realize the...
Okay, so I think that's going to answer my next question.
Yeah.
So if instead of considering these outer red dots to be gauge qubits, you fix their values.
Yes.
So you know what they are.
That's right.
So that's kind of like this.
That's kind of like this. It's not quite as good because then they stop being perfect tensors.
Right.
So that's why we did it the other way.
Okay.
Yeah. So, but I mean, I think if you were trying to build a quantum computer along these lines, probably the thing you would want to do is do the one where you have a central pentagon and everybody else is a hexagon.
Sorry, maybe I didn't follow this. So if I put the box qubits in a direct product state, then the resulting state you get, does it satisfy the RT formula?
Almost. Yeah, maybe I should comment on that actually. So if you take the version where everybody is a hexagon, so you just take a hexagon tiling and you contract all the indices, now you've given up the subspace, so it's not useful to think of it as a code, but just one state. So we call that a holographic state. That one obeys Rutakinagi exactly for connected boundary regions. So it saturates the bound.
What happens in the disconnected?
In the disconnected regions, it can't work exactly, and the reason is because there's correlation. So as you know, right, when Rutakinagi is correct at exactly, the leading order piece, then the mutual information is 0 between sufficiently separated regions, right? So in the bulk, that's fixed because there's a 1 over n correction. But if we were asking it to be exact, then it would mean that there couldn't be any correlation, say, between like something here and something there. And that's wrong, right? I mean,
in your model, you have correlations.
Yeah.
Then with a single pentagon and all the hexagons, aren't you just essentially making a flat cone?
No, it still grows exponentially because it has to do with how you contract the hexagons. Okay. Yeah, you still arrange. It's more. It's growing very fast, faster actually. That's part of what makes it better. Yeah.
So if I were to think about just this instead of, and I don't understand anything about AdS, CFT corresponding, how much of the picture am I missing?
Well,
what's the most important thing that I'd be missing?
That if you didn't know anything about AdS CFT, well, probably just you wouldn't have come up with these codes, I guess. I mean, once we come up with them, we can just study them like any other codes. Yeah, I mean, maybe if you were smart enough, you would have come up with them. But for us, it was thinking about AdS CFT.
What I mean is, okay, how much of that picture is captured here, and what's missing?
Oh, you mean to get the full AdS CFT? Yeah, so that kind of has to do with this list that I gave. Oh, I see. So you're asking if I'm a lazy computer scientist and I don't want to learn about CFT, and if I learn about this code, then can I view that as understanding AdS CFT? Okay, good. I gotcha. Yeah. So then we have to go back to this list here.
Yes.
Right. So indeed, I think probably the two things which annoy me most from the point of view of trying to use this as a model of AdS CFT are that this thing with the sub-AdS locality. So I've sort of mutilated the geometry. So it's local only on scales that are large compared to the radius of curvature. Whereas in the real AdS CFT, we should be able to like build the LHC or something. I mean, the cosmological constant could be, the size of the universe, and we should be able to do local particle physics, and that should work. But here, I've just sort of lumped that all into a single tensor where I've given has no internal structure really. So that annoys me. So if you like, there's no hierarchy between the Planck scale and the AdS scale. So that's one annoyance. Actually, for me personally, this no bulk diffeomorphism invariance is actually the other thing that's really annoying. So, so for example, you would think that, well, here's a confusing fact. So any operator in the center of the bulk here is going to commute with local operators at the boundary in the code subspace. But you would think that if I just act with an operator that creates a baseball or something in the center of the bulk, it should increase the energy of the state. Because now there's a baseball, so it's an excitation over the ground state. But how can that happen? Because the Hamiltonian is the integral of the stress tensor around the boundary, which is a local operator. And so in order for a local operator in the middle of the bulk to raise the energy, it must not really commute with all the local operators at the boundary. There must be some, if you like, gravitational Wilson line or something going off to infinity that clicks when you act with this operator. And so that is part of the machinery of AdS CFT, but it's just lost in this discussion here. So,
isn't that saying when you project the Hamiltonian to the code subspace, now it's not completely living on the boundary? It has a component in the bulk.
Yeah, but that's not true in AdS CFT. I mean, that in AdS CFT, the Hamiltonian is a boundary integral. And that is a consequence of diffeomorphism invariance, which is just sort of not very clear here at all. So it's some feature of gravity, being a diffeomorphism invariant theory, that I would like it if I could somehow put it into this model. It would make me feel happier. But nonetheless, I mean, I think zeroth order maybe you can do what I said. You're allowed to think that.
And what was the other side of this? So what became clearer about AdS CFT now that you have this? Did anything?
Well, I think there's this whole religion about geometry emerging from entanglement and so on and so forth. I think this is by far the most controlled illustration of that. Where you really understand everything. I think also there's this debate that Bartek alluded to about the causal versus the entanglement wedge, which I don't really want to get into, but these sort of ideas are, I think, strongly favored the entanglement wedge. I don't know. I think also just understanding better the interplay between, right? I mean, one beautiful thing about quantum error correction is there's this interplay between having a preferred tensor factorization of the Hilbert space and having a subspace, and when those two sort of don't play well together, then it's actually very interesting. And so to see that sort of interplay is going on in AdS CFT, I think is helpful for understanding how is this bulk really emerging.
So in some sense, you do have a Hamiltonian for the boundary. It's just very non-local, right? Because you have a stabilizer code and you can write down the generators. Should we interpret part of the message of AdS CFT that there should actually be a low density parity check code with local operators acting on the boundary that will have generate a code?
No, I actually, so this is part of a fight that I was having with Joe Polchinski for a long time. I don't think you should think of this as being a low-density parity check code. I mean, it has to do with the question I asked Daniel, right? Because this is a one-dimensional model. So if I tried to make it with really local stabilizers, a stabilizer group that was generated by local operators, it wouldn't work. Like I wouldn't be able to get the kind of thing that I'm having here.
It isn't. But I was asking, because we know AdS CFT actually works, right? Yeah. If we discretized all of that, would that actually be some kind of local low-density parity check code with similar error-correcting properties?
You're thinking about it in a code in a different way than what I was saying here? I mean, here it's clearly not a low-density.
Right, but in a CFT, it's a local Hamiltonian.
But it's the integral of a local operator. It's not. You don't get to say that. You don't get to impose the stress tensor separately everywhere as a constraint. It's only the integral that right, and that's very important. I mean, that's why you can have long-range entanglement.
That's only relevant if it's frustrated.
Yeah. It means the terms do not commute with each other. That's the necessary, right? It cannot be.
The local Hamiltonian is a sum of local terms. That's like an integral.
Another timeout. Frustrated? What? Who? Where? Can you guys?
I'm frustrated.
So if you have a bunch of local constraints,
yes.
And the Hamiltonian is a sum of these local constraints, and you have a ground state that satisfies all of them, that's frustration-free. Okay. Now, if the ground state can't satisfy all these constraints, that's frustrated because some of them get. So this.
Yeah, so I don't think that the ground state of a quantum field theory is not annihilated by acting with the stress tensor at a point. Okay, true statement.
Isn't frustration what produces the entanglement in the ground?
Not necessarily. I mean, if you look at actually basically any quantum error correcting code, they're very entangled.
That's not good enough though, Steve.
This is a. I don't know if there are proof, but this sounds reasonable. Is there a proof that a CFT cannot be a ground state of a commuting projector Hamiltonian? CFT ground state?
Yeah, I think that's pretty clear because it has too much long-range entanglement, right? I mean, so actually, I mean, we actually gave a proof. So in our paper, we gave a proof that in the context of stabilizer codes, unfortunately, which I'm going to use the term again, that this fact that you can reconstruct stuff on disconnected regions is impossible if the stabilizers are locally generated. That's easy to prove.
So I have a somewhat naive question with that picture in mind, which was, if I understood correctly, the whole role of that network was to push out a local operation on a single qubit and show that it sort of acts on many many parts of the space. Right. So I don't really see the tensor constraint of the individual tensor seems rather heavy for if that's the property.
Oh, you mean the perfect? Yeah, right. So that was the comment that I made, that this pushing really only requires the tensors to be invertible, not to be perfect. But the thing which requires them to be perfect is if you want the entire tensor network to be an isometry from the ingoing bulk legs to the outgoing boundary legs.
Why is that? Just from a.
It's just convenient. No, I mean, I mean, so this was a comment Douglas was making earlier today. I don't think it's necessary. It just makes for a simpler model. It makes for something where you can write everything on a T-shirt. Well, but you could easily not have them be. You could. What you would do if they were just invertible is you would push all the states through, and then you would just take their linear span and call that the code subspace. And I think it would be fine.
If you want the dangling legs to represent some sort of physical degrees of freedom.
That's right. Yeah.
Presumably you want that.
You want the isometry. That's right. So we wanted to have a simple. I mean, we wanted this picture that a local bulk operator here is really just an operator on this dangling leg. In that I wanted the operator here to commute with the operator there, and I wanted that to be preserved, pushing it through the map.
Okay, thank you. So, thank you.